Okay, so hello everyone. Thank you for participating in this webinar. And my name is Junner Zhu. I'm currently a postdoc at MIT, working jointly in mechanical engineering and chemical engineering. So today I'm so happy to be joined by three young talents in the area of data-driven modeling of batteries and energy materials and systems. So they are my colleagues, Wei and Hongbo from MIT, and Steve from Imperial College London. As you know, battery is such a complex man-made system involving multiple scales and physics. So our speakers today will cover a wide spectrum of topics. So hi, Wei, Hongbo, and Steve. Let us follow. I suggest that we follow the agenda in the poster. So we will start from Wei, and then Hongbo, and close with Steve. Each of you will have 20 minutes, followed by 10 minutes Q&A. After all the presentations, we will have a panel discussion. So I would like also to encourage the audience to raise your hand to ask a question or simply type your questions down in the Q&A panel. So today our first speaker is Wei Li. And let me, Wei Li is currently a postdoc. Actually, he is my lab mate, and he's also in the Department of Mechanical Engineering at MIT. He received his PhD in engineering from School of Vehicle and Mobility, Tsinghua University, in 2019. His research interests include mechanical testing and modeling of materials and structures, multiphysics modeling of lithium batteries, and physics-informed neural networks. So Wei, the floor is yours. You can start sharing screen and start your presentation.
Yeah, thank you.
Wait, can you open your camera?
Okay, yeah. So I'll show my screen. So thank you, Gina, for the introduction. My talk today will be like the physics-guided machine learning methods in the application of battery modeling. So I will talk about maybe 3 different examples. The background of our research is about the crash safety of lithium-ion batteries. So as you see here, you may find a lot of many crash accidents of electric vehicles. So I listed 4 of them. So in all these cases, we can see there's a severe mechanical deformation. And this will potentially damage the battery and lead to this fire and explosion. And we can clearly see this from this simulation study. And this is actually a full vehicle impact simulation of a side impact into a pole. And if we look inside the battery pack, we can see there is a very large local deformation here. So this will probably damage the battery. To understand this mechanism, how the mechanical deformation leads to the battery failure, we need to do some tests on cell level. For example, we can do indentation tests on a single, this is a pouch cell. And if we cut the battery after test through the indented area, so we can see the cross section inside. So firstly, we can notice the battery is actually a layered structure. So they are basically the anodes, separators, and cathodes. And then we can see 2 kind of fracture patterns. So one is the very localized fracture under the indenter, and also somewhere far away from the indenter, we can see a through thickness shear fracture. So this is basically the 2 different fracture patterns. Of course, a better way is to do a CT scan. So here shows the CT scan of 2 different loading cases. Also from this case, we can see some localized deformation fracture. And for this case, this is a different loading case. We can see a through thickness failure. So in this kind of fracture patterns, so the separator will fail, and then there is a very high possibility that the anode and cathode will be in contact, and this will lead to the internal short circuit. So this is another research. So it's actually an in situ X-ray experiment. So we can see the whole process of a layer penetrating into a cylindrical cell, so that we can also see the fracture here and the internal short circuit area. And this brown color shows the chemical reaction after internal short circuit. So in summary, like the mechanical abuse or mechanical deformation, it will induce the internal short circuit after the fracture happens inside. And after internal short circuit, there will be like the electrochemical reaction, and these reactions will release a lot of heat. So this will eventually lead to the thermal runaway or the fire and the explosion. So in my talk today, I will mainly focus on the mechanical part, and the next presentation by Hongbo will probably focus on the electrochemical part. So like to model or to predict this kind of fracture, we need to develop a very detailed finite element model. So as shown in this figure, so this model resolves each layer of the structure inside the battery. And the difficult part is actually how to calibrate each of these components. So in this battery, we have a total of 5 different components or materials, and they need to be, because they are quite different, so they need to be calibrated by different material model. And then like after calibrating all these material, we are able to predict the force displacement curve. And also most importantly, we can predict the fracture pattern here. So this basically proves our model is quite like accurate. But like, of course, in this model, we didn't consider the electrolyte inside the battery. And actually, the electrolyte has some influence on the mechanical performance. For example, if we do compression test for the grand battery like this without the electrolyte, we can see the response are basically the same. But if we do the same test for battery with electrolyte, then we will see a strengthening effect when we increase the loading speed. So like in order to model this effect, we will need the polar elasticity theory. So except the contribution from the solid skeleton, we also consider the pressure from the fluid. And for the mechanical, the solid part, we will use the model we developed before. And for the electrolytes or the fluid flow, we need like a Darcy's law to describe the fluid flow. And in these two parts can be connected by some continuity equations. So with this theory, like we're able to predict this strengthening effect. So this is basically our like physics models for this problem. But if we want to use this data model to predict like in a full vehicle scenario, this model is like too detailed. The computational time will be too large. And one possible way is to do a homogeneous model. So which is we further homogenize this data model, then the computational efficiency can be increased. Of course, with this homogeneous model, we can also predict the fracture, but we need to like recalibrate this model. So this is also some extra work. I guess this problem is common for many engineering systems. So as we go to a larger scale, we need to a more homogeneous model, and this can increase the computation efficiency, but also at the same time we will lose some physics behind. So we are thinking maybe if we can use the machine learning tool to scale up the this phenomena, like to increase the computation efficiency, but also like remain most of the physics. So for a typical machine learning algorithm, we need to divide the input and output, and we try to like parameterize our problem. Like if we consider an impact from a random direction of some random mass and angle, and also with a random shape, then maybe we have these 7 different parameters as the input, and we want to know like, if the battery will fail in this case. So after we parameterize this problem, we can generate data from our detailed model. So basically, we run around like 2,600 cases, and then we prepare the simulation results. So this will give us some data for the training, and for one model, we can get the calibration results. Quantification result, like with this model, we can tell under certain condition if the battery is safe or it will short circuit. And also for those short circuit cases, we can do a regression model. So this can tell us like under this condition, what's the maximum intrusion. So this is one example. These some details about these examples. Like this is the simulation results. We have like the red represent the short circuit case and gray represent the safe cases, and also for the other cases. So after learning, we can see the envelopes is basically consistent with our input data. And also we can do a regression model as mentioned before. So with this example, we can see the power of the machine learning algorithm. It can give a very good fit to our data, but the problem is also that we need a large data set in order to make sure the accuracy is accessible. But this year it takes a lot of time. Even for the simulation, we need a lot of time to prepare the data. So people are thinking maybe we can introduce some physics into this framework, so we don't need that much of data. So this idea is maybe not. This is one of pioneering work in this area by Russell et al. So they try to solve the Stoker's equation with some, they call it physics-informed neural network. Like without experiment data, if we know all the physics, so they can solve this equation with very high accuracy. And another research is by Nu et al. They actually made a good summary of this physics-informed neural network, and they have implemented this algorithm into a package, so we should available to everyone. So we are thinking like if we can also use this tool for our problem. Then we try the first case of a plate deformation. So this is only a plane stress tension with some like non-uniform stretching force. Like for conventional or for purely data-driven methods, we may need to know the outputs or some exact solution of this. For example, in this case, the displacement fields. And then we try to minimize the noise so we can have a good fit of the exact solution. But for physics informed framework, we actually don't need the exact solution. We need the network to satisfy these equations. And for example, this one represents the force equilibrium along two directions and also some boundary conditions. But you can also see here, in order to calculate this term, we need to first calculate the stress and strain from a displacement field. And then if we try to minimize the loss of all these terms, this neural network can satisfy this physics laws, and then it will be a good approximation of the exact solution. So this is the result, comparison of the finite element simulation and the neural network prediction. We can see there's a good match. So since this method works for this 2D solid mechanics case, here is more details about this method. So I probably will quickly skip this. So the same method can be applied to the polar elasticity theory I mentioned before, but in this case, it will be more complicated. The input will be time independent, and we will have a pressure field comes from the fluid, and the mechanical, the physics part will also accept the mechanics of solid phase, as mentioned before, the force equilibrium and the boundary conditions, and together with the initial conditions. We also have the equation for the fluid. So this is the governing equation for the fluid flow, and we have some boundary conditions and also initial conditions. So this, so similarly, if we can minimize all these terms, then this neural network prediction will satisfy the physics we know. And also here is a summary of all the details. So we can see these two equations are coupled by this term, and this actually represents the contribution from the solid part. And I also want to mention that since this is a very complicated case, we have a lot of loss terms, and the loss ways. We also have a lot of loss ways to formulate the total loss, and this will be some extra hyperparameters we needed to. And after training, so here is the finite element solution for this uniaxial compression case. So we can see the pressure distribution is actually uniform through thickness. And so neural net prediction is actually quite similar to the FE simulation. And if we compare the distribution along X direction, we can see it correlates well, but there's still some discrepancy. So this is actually due to the limitations of this framework. Like if we look back at the framework, I actually didn't briefly mention the coefficient, the weights here. So these parameters are actually very difficult to determine. And I guess this and this will probably the error comes from how you determine how well you determine these coefficients. So we are thinking how can we improve this framework? Then we come up with the idea, maybe we can replace the whole PDEs and boundary conditions with some energy-based laws, because this PDEs is actually equivalent equivalent to the principle of minimal potential energy. So in this case, if we use the potential energy as naught, we can directly minimize this energy to get the right solution. So if we look at this example again, so this is our prediction before, and after we use the minimal potential energy, we can also get a very similar result. But if we try some other cases, for example, the central hole tension, so we can see for the PLN I mentioned before, it actually fails to predict, accurately predict the stress concentration here. But for the potential energy-based method, we can successfully predict this stress concentration, and the similar phenomena can be seen from this three-hole tension. So for this method, the prediction, so it basically predicts distribution, but the concentration factor is not correct. As for with potential energy method, we can get a better result. But this doesn't mean this method cannot get a good accuracy. It's only because the parameters are very difficult to tune. And then we also try this energy method with some out-of-plane cases. For example, the out-of-plane deformation with the plate, and even some balcony analysis. Like if we compress a thin plate from the in-plane direction, it will buckle to out-of-plane shape. So with the energy-based method, we can also predict this kind of problem. Similarly for another different node condition. And lastly, I want to conclude my talk with a summary of the physics-guided machine learning concept. Like there is actually not no clear definition of this physics-guided machine learning, and people are using different terms. But basically, if we look at the machine learning algorithm, there are three important parts: the data, the model, and the training rules. And if we want to implement our physics into this framework, it can be like one of these three. So for the data, like if we use a physics-based data set, then our model will also learn this physics. So as in our first case, so all the data from are generated from our data model. So the accuracy is actually highly dependent on the FEM model which we develop. And the second part is we can introduce some physics into the training rules, like the loss functions, which I introduced before. So like in the first case, in these two cases, both these two cases can fall into this category. And like the last part is the physics-guided model. So maybe we can design this model based on our actual engineering problem. So these are basically the summary of this concept. And I didn't give like very clear conclusions from my presentation because I guess there are still a lot of open questions, and I guess we have a lot of we can do on this area. So it's still too early to draw some conclusion from this. And I guess with this, I'm going to end my presentation. And I'm happy to take any questions or suggestions from you. Yeah. Thank you for your attention.
Thank you, Wei. So I think there is one question from the audience, from Kyle. So the question is, how did you choose the weight of different terms of loss?
Yeah, that's exactly the problem I just mentioned. Actually, I don't have a very good way to optimize these loss weights. Like I just do a basically like a parameter study or matrix. Just try and see the result and try another combination and see the result. So yeah, that's a problem, but I guess I don't have a very good solution to this. So except the trial.
Yeah, actually, based on this question, I also have a question. I know very well because we co-authored the paper, we work together. But I have a question about how much time did you spend? I mean, to train one neural network for example, for in-plane simulation.
Right, for like the actually training, it may take like half hour or 1 hour, but you may actually need much more time to tune these parameters.
Okay, and there is another question, I think, and then we can move to another second talk. And the question, oh, sorry, there are two. So one is from Xueju, and do you need to consider the charging and discharging status of battery materials and therefore the chemomechanical coupling in the method, in the model?
Yeah, like the state of charge or the SOC actually, yeah, have some influence. But I guess we have some other research on this topic. Yes, we can include the state of charge dependence into our physics model of FEM model. But for currently, if you want to model this effect with this neural network, is still difficult, still a long way to go.
Yeah, I want to say this is still a long way to go, and Xueju herself actually is an expert on this. Okay. And there is another, I think today Steve still has not shown up, so we may have more time. Oh, Steve is here, sorry. And then we will, yeah, Steve here, and sorry, Steve. And then I think there is the last question. So you mentioned that machine learning model can perform similar as simulation. May I know, is there any data to show this result? R2 score or MSE? Another model you mentioned, it depends on the time series. How do you model this?
So for the time series, like I guess there are actually two different frameworks or two different strategies for a time-dependent problem. Like in this problem, I directly treat the time as the input. So some researchers call this a continuous framework or strategy. So the time is actually is treated as the input. And also you can use some other maybe recurrent neural network to include the time influence into the structure of the neural network. I guess that's two different strategies. I'm not sure what's the first problem about.
I think we can move on and leave this question to the panel discussion. Probably the audience will have more interest. Okay.
Okay.
So, okay, thank you, Wei. And our next speaker is Hongbo, and yeah, Hongbo is currently a PhD candidate